Tonight's presentation will be exploring globular clusters. Globular clusters are a natural congregation of stars born together in primeval clouds of hydrogen and helium in the early parts of the universe. Globular clusters from the time of discovery in 1665 through the analysis of extragalactic globular clusters with the latest space telescopes constantly provide new information about the earliest stages of the cosmos and the evolution of stars. Despite the latest results of scientific data and spectral insights into these fascinating structures, there are many unknowns and mysteries about globular clusters. The continuous discovery of globular clusters in the Milky Way galaxy is a hot field of astronomy, even in the 21st century. So the presentation tonight will discuss the history of astronomical analysis of globular clusters, from their discovery to the latest information and theories about the nature of globular clusters. Tips and methods for observing globular clusters will be part of the discussion, combining photographic and spectrographic analysis to reveal the mysteries of globular clusters. A little bit about our speaker, Justin McCollum. He is a graduate of Portland State University with a Master's of Science in Physics. Since 2005, he has been a physics laboratory coordinator and departmental astronomy instructor. And I think it was at Lamar University, if I understood. His accomplishments including graduating at the top of his cohort in the postgraduate certification on artificial intelligence and machine learnings with the University of Texas Austin's McCombs School of Business just last month. Justin has also volunteered at the Georgia Observatory since 2005 and has served in different club officer positions in several of the area astronomy clubs. So without further ado, I will turn the floor over to Justin McCollum. And again, if you have any questions, please put those in the chat and we will cover those at the end of the presentation. So Justin, it's all yours.
Thank you, Chris. We'll go right into, and thank everyone here for joining the meeting for tonight. We're going to go into exploring globular clusters. And let me just start my presentation here. So this is actually a picture of Bade's window, which is sort of an open gap in the Milky Way looking in the direction of Sagittarius. We got two examples of some globular clusters here. I don't know if anybody's ever seen these, but the bottom, I think, is NGC 6522, and the other one is 6528. One thing about globular clusters is that they are just large congregation or islands of stars. How do they differ from open star clusters, where you're going to have a lot more of them? They're going to be closer together. They're more bound together by gravity, and they were formed together, just like open star clusters, but very early in the universe while the galaxy was forming. Most globular clusters have a spherical shape. There are some elliptical structure to globular clusters, but they're very rare. They're very old. Most of them were formed around the time that the Milky Way galaxy was forming. So you get a protogalactic cloud, a cloud that forms the galaxy, and bits of it will split off and break off into sections, and those will form the globular clusters. They're very ancient. They usually have a low concentration of metals, but there are multiple generations of stars that will form in a globular cluster within the first couple billion years of their existence. But they're very efficient in star formation. So once they've used up a lot of the gas to form the stars, they will form those stars very, very quickly. So the star formation period is very, very short. It's very quick, but a lot of the stars are formed very quickly. And they'll have anywhere from a few 100,000 to several million stars. Many of them are almost like borderline dwarf galaxies. They're poorly understood. There's a lot about globular clusters that are not well known. A lot of astronomy has been focusing on exoplanets and looking at the early stages of galactic evolution. And globular clusters still require a lot of study, extensive study. And many of the star populations within these globular clusters sort of match the types of stars we find in galactic bulges that tend to have older stars. Those are in the spiral arms of galaxies. well, not in the spiral arms, but in the galactic bulge, in the core of galaxies. And also we find those types of stars that are prevalent around elliptical galaxies, the more redder, older stars. Now, the first globular cluster, anybody know when the first globular cluster was discovered? Well, the first one was discovered by the German amateur astronomer Johann Abraham Ahe, who in 1665 found M22 on the same night he was looking across the sky in Sagittarius to observe Saturn in those first decades that we had telescopes after Galileo. And the great Sagittarius cluster of M22, he came across it. Now, unfortunately, none of his work has survived, so we only know that by secondary sources, but this is sort of a drawing of what that cluster would have looked like. This came from the publications of William Herschel, and these were the time of observations between December 1783 and April 1785, when he was at the peak of his observing period. We can see the little dots around here. It's somewhat comparable to the types of drawings people will make. We have a photograph down here of M22. Here's Sagittarius, here's the teapot, and that globular cluster is right up here. We also have another one, which is M28, also right here. These three down here, 54, 69, and 70 are globular clusters, and I think M55 is also a globular cluster. Now, continuing on, one thing about these globular clusters is that in the early days of astronomy, particularly when we have professional astronomy after going into this 17th centuries, astronomers, all they knew about the universe was the planets, the stars, and comets. Comets were the thing. Planets were predictable. And yes, moons were being discovered orbiting around Jupiter and Saturn, and later on the moons Phobos and Deimos of Mars, but comets were the big thing. And this French astronomer, Charles Messier, well, he formed the Messier catalog of these 110 objects that he came across, but he was not looking for these fuzzballs that didn't move across the sky. So he plotted these objects to avoid looking at them again, because he was really looking for comets. Now, he had a lot of contributors. The one I have here in the light colors, like Deschazaux, Hodernia, Kirch, Johann Kohler, Johann Bode, all of these individuals right here were the greatest contributors to the discovery. So he didn't discover all these objects. He had a lot of help, and there were a lot of rediscoveries. And many of these happened before Messier. And we have some ancient people like Aristotle and Ptolemy, particularly with the Messier 7, the sort of the, I like to call it the flocking bird nebula, the flocking bird open star cluster, or the wild duck cluster. And that was visible to the naked eye. Other objects would be added on from 1921 to 1967 based on looking at older data by later astronomers, and that verified the catalog up to 110 objects. Now, why do I talk about this? Because a lot of these fuzzballs, a lot of these Messier objects are globular clusters. So here are some of the earliest work from Charles Messier. So you have to see what these fuzzies looked like in the telescopes. Now, they didn't have glass mirrors. What they had was speculum mirror, which is basically a sort of a copper tin alloy mirror that's nicely polished. So here we have M31, there's 32 and 110. Here's the Orion Nebula. This would be comparable. This is a sketch of what he would have seen with M15. Here is a more up-to-date photograph of M15. And this comes from his workings. This is a picture of his original writings. And right here in the medieval French, well, sort of the medieval French here around the 17th century, there's where we have Messier 15 recorded, and in the old-fashioned sort of coordinates of right ascension and the declination. And that's Messier, his signature right there. So we have this a recording and confirming that it is a grouping or a ball of stars, as we see here in the image. Now, later on, as we move into from the 17th century into the 18th and 19th century, hopefully everyone knows a lot about William Herschel. These are many of his drawings. We have what we later learned to be nebulas, planetary nebulas, galaxies, open star clusters. Well, open star clusters would be trying to find one like right here. And then we have two globular clusters here. We got another pair of globular clusters here. He's had a lot of unpublished work, but basically between 1802 and 1820, there's about 7,500 of the messy objects that we know. He built over a dozen scopes. This is one of his more famous ones, the 20-foot scope. So he had about a 19-inch speculum mirror. It's about 2/3 copper, 1/3 tin. You mix it with like silver and antimony. It's a white brittle metal, but when you polish it, it's nicely reflective. And between 1783 and 1790 was most of his intense discoveries when he was just scanning across the sky back and forth, just plotting these objects night after night. This was his big 48-inch scope. This is one of the two mirrors that survives. You can see that reflective surface. We call this a Herschelian telescope because he would basically have the mirror tilted. He would take sort of a little glass refractor and look down into the tube and magnify the objects to observe them. It was basically, each mirror was an f10 focal ratio. The length was 40 feet. The mirror was about 48 inches in diameter. And this was the largest telescope in the world for 50 years. For 50 years, it was the premier telescope. Now, one thing is this great debate between two famous American astronomers, Herbert Curtis and Harlow Shapley. Both of them were arguing about the size of the Milky Way galaxy and whether or not the Milky Way galaxy was the whole universe. So what does this have to do with globular clusters? One thing was how these globular clusters were plotted around the Milky Way galaxy. See, Shapley was correct about the size and structure of the Milky Way that we know today, but he was incorrect in thinking that the Milky Way was the entire universe. Whereas Curtis was right about the whole universe in terms of there was more to the universe than just the Milky Way. There were other galaxies, but he was incorrect about the size and structure of the Milky Way. The term spiral nebula is what referred to galaxies. Later, the term island universe was applied. And then we have galaxies. And this concept really came into fruition in the 20s and the 30s. So it's really just about a little over 100 years old since we were aware that there were other galaxies other than the Milky Way. Now, coming to here is Shapley's map here of all these little green dots. All these little green dots are plotted around this X square right there, which is the center of our galaxy. This is an older map made by Arthur Eddington, which placed the Milky Way about 60 light years above the center. Here's William Herschel's work. This is where, if we go back to this man, Curtis, this was his view of the Milky Way. This was a pretty strange view where we had the sun in the center of the Milky Way and everything was lopped over to one side. Well, we now know that based on plotting how Shapley plotted all these globular clusters, it gives us a more accurate model of the Milky Way galaxy. That is, we're at the edge rather than at the center. Now, we have over 200 known globular clusters now in the Milky Way, and we can see how the amount of metals have changed in the globular clusters. So we go from 10% of the amount of metals that we find in the sun down to about 1/10 of 1% of the amount of metals that we would see in the sun, meaning that most of the stars here are going to be hydrogen and helium stars. They're not going to have a lot of elements that are going to be heavier than helium or carbon. There's the Carmongo catalog, which was basically from 2016 to 2018, looking at 1,100 new objects for new star clusters and new globular clusters candidates. And these are 5 right here. So there's possibility of hundreds of new undiscovered globular clusters sort of hiding around in the galactic bulge or very close to it. So 5 of these are the 5 right here. This one here is 1. Here are 2, and here's another 2. So we've already added more globular clusters into our catalog for the Milky Way galaxy. And it's likely that the number will probably increase by at least another 100. Now, the size range, they can be anywhere from a few dozen up to about 1 million light years. When they're a million light years across, like Omega Centauri, they could be the remnant of a dwarf galaxy when material gets torn off. In terms of the size, most of them will be between 20 to 110 light years, but there are some that are a few hundred light years across. Number of stars will be over 100,000. Many will be between 100,000 and 500,000 stars, between 8 to 12.7 billion years old. And right here, I found one estimation to be around 169 for most official websites, but there's another 200 candidates. But some galaxies have well above 10,000 globulars. So there are some big galaxies that will have tens of thousands of globular clusters. Now, many of them fit within the population 2 stars, meaning they have not a lot of metal. So we would not expect a lot of planets that are terrestrial planets to be orbiting many of these globular clusters. If they have planets, they could be more like gas giants. So the high density, the stars are very close together. You can have anywhere from 4/10 per cubic parsec, increasing from the edge of the globular cluster up to 1,000 stars per cubic parsec. So they're really tight. They can be less than 1/10 of a light year apart from each other, versus the 4.5 light years between the stars in our own local neighborhood. So they can be very packed together. Now, this is the Shapley-Sawyer classification system. It's very simple. We go from 1 to 4, 5 to 8, 9 to 12. So really the stars are very concentrated at the center. And then what we do is that we have a less concentrated outer area and a more concentrated central region, until basically the center itself loses its concentration, becomes very, very dispersed. And a lot of globular clusters that are in the process of sort of congregating together, started becoming condensed together, are going to follow more in the 12 category. This is actually one of the Harvard, I think this is Harvard 20, one of the Harvard 20 or the Trump, no, not the Harvard 20, but one of the Trumpler globular clusters that look like faint little smudgies, but we can see the details in the stars towards the center. If you type in the Shapley-Sawyer classification system, there's a classification system for identifying and categorizing open star clusters. Well, we have that for globular clusters. Now, populations of globular clusters, they're what we call the Osterhoff groups. The Osterhoff type 1, like Tarzan 7, is a metal rich. So it has higher metal concentrations, higher amounts of metals with respect to other stars and other globular clusters. The type 2 it has very poor amounts of metal, but there's a lot of the R Lyrae variable stars. So they're stars that flicker. And many of these globular clusters, when they approach towards a major galaxy, it's likely they were once something like a Magellanic cloud, like a little galaxy with dust and gas to form stars, but the material gets torn off or pulled off by gravitational tug of war with the larger galaxy. And so we end up having these globular clusters as the remnants of some of these dwarf galaxies, not all, but some. And some of them face an evaporation rate, meaning that some of the stars can be pulled out of that globular cluster. So globular clusters can lose stars to the galactic halo, or they can be swirled into the larger galaxy. So the possibility of galactic cannibalism, well, globular clusters can be cannibalized by larger galaxies. Few of these globular clusters do indicate having intermediate massive black holes, and we'll talk about that a little bit later on. This is one of the globular clusters in the constellation of Ara, so that's an Osterhoff type 2. Now here, most of our globular clusters usually lie outside the galactic plane and lie within the galaxy's halo. But with the Carmongo catalog, that may change as we see more and more of these globular clusters and globular cluster candidates concentrated within the galactic bulge, where we expect a lot more stars. They're highly elliptical orbits with orbital velocities varying between 400 to 500 kilometers per second in terms of their motion as they go around the center of the Milky Way galaxies. Now, there are some cases where some of these globular clusters, if they're close enough towards the galactic center, will be moving in retrograde motion in opposite directions. So some will move in opposite directions, some will move in the prograde motion, meaning they'll move in the direction of the galaxy's spinning axes. Some of them will move in the opposite direction. And it gets a bit more organized towards the center in terms of the orbital patterns, but out here, the orbits are more inclined and it's a bit more chaotic. Now remember, we have a lot of dwarf remnants. We tend to find a lot more of the main sequence stars out here and a lot more dwarf remnants in the center of a globular cluster. So as we pierce in, we see white dwarfs, we'll see neutron stars, we'll see pulsars. And in some cases, some globular clusters will have constellations or clusters of black holes. And we're talking black holes of 10 to 100 solar masses. So you get solar mass black holes formed from stars, they merge together, and so you get a lot of these little massive, supermassive, well, not supermassive, but these much more massive black holes that reside close towards the center of a globular cluster. Now, one way to distinguish about the globular clusters is we rarely see any stars forming these globular clusters. So we have what we call the cutoff sequence, because we don't get any of the A and B and O class stars that form all that much in globular clusters. You get the stars that end up being the M, the K, and the G class, maybe a little bit of the F class, and then we get what we call this turnover, where basically any of these stars end up shifting into the red giant branch, where they start reaching the end of their lives. The only case where we see stars forming in globular clusters is where the stars collide together inside the globular cluster, and they form these fresh, young, beautiful blue stars. We call these blue stragglers. I don't know if anybody's ever seen blue stragglers in a globular cluster, but you can see the blue stragglers. We have some here, we have some there. And when we look at the blue stragglers, there they are, right here, right there, right here, right there. And then we see some of these blue stragglers. We have some helium white dwarfs. We have some cataclysmic variables. It's only when a globular cluster is moving through the plane of the Milky Way that we have all of these stellar associations with their own local centers of gravity, really pulling on this gravitational tug of war and knocking around like pinballs, knocking around all these stars like balls on, let's say, on a pool table, and they smack together, they collide together. There'll be the occasional planetary nebula forming in these globular clusters, but you'll get those blue stragglers that will form. The one thing about globular clusters is that all the radiation gets, a lot of the dust and gas gets pushed away, and we don't have any star formations taking place after a couple billion years in these globular clusters. So the stars are getting redder, they're getting older, except for the occasion where we get these blue stragglers that are forming, and they tend to form very deep inside the interior of the globular cluster, where the stars are more likely to smack together because they're closer together, they're more concentrated, and the gravitational effects will be much more, you'll have a lot more stars colliding together to form these stragglers. Now, we have two scenarios on how globular clusters will form. It's either what we get today is that we have a constant mass, and basically what happens is that we get the more massive stars forming and the lesser mass stars that are forming more evenly distributed around the globular cluster. Then we get highly energetic radiation. We get a lot of radiation from these very bright stars that start to eat away at this dust and gas. And what we get is that we have the first generation stars here. Of course, the very massive first generation stars will blow apart, and their material will form a second generation of stars. And what's left of any material that doesn't form these stars gets blown away, and we have this sort of more homogeneous, where we have uniformly distribution of the one generation and the two generation stars. The second scenario is the mass segregation, meaning that we get more of the massive stars towards the center and the lesser stars out towards the edge. Then we have all of these stars blowing out and forming the second generations of stars. The first generations of stars that are of low mass pretty much will live forever. And we have the same situation over here with scenario one, where basically instead of having all of these supermassive stars all spread out around the globular cluster at first in the first generation, you can see they're more concentrated towards the center. But regardless of where we have the blowouts towards the center of the globular cluster or distributed around the globular cluster, we're still going to have this peppering of these low massive stars of the first generation and low massive stars of the second generation, and no more massive stars. And we have to realize with low massive stars, they tend to have very long lifespans. They tend to evolve into the T-Tauri stars. So they can be pulsating stars within a globular cluster. The more massive ones will form the OB stars, the very massive stars, these O and B class stars. And where they form, they'll either form towards the center or they'll form in layers where they're less dense out towards the edges. And when they blow apart, eventually after a while, they look like a young superstar cluster, very hot, very bluish stars. And over a while, they'll start to age into the red color. And that's where we get into our globular clusters. So a lot of these globular clusters start out as these very hot superstar clusters. Now, we've got multiple populations that form over a period of 2 years. So we get our more massive stars. The massive stars will die out. We've got a balance between the gravity pulling things in, due to the overall mass of a globular cluster, and the radiation wanting to push the globular cluster outwards. Sort of the same circumstance which is keeping a star stable. We got the radiation of a star that wants to swell it, but then the gravity keep a star together. Then the black hole over time will spread out, and we end up having the next generations of stars that are forming in the globular cluster. This becomes the second generation, where a lot of these massive stars will blow apart. We have a new range of star formation taking place, and we get 2 generations of stars here. We get the first generations of stars that tend to have a bit more oxygen than iron, and the second generation has a bit more sodium than iron, because the oxygen forms in the first generations of stars, but to form the sodium, you need to have higher temperatures. So those hotter stars blow out the sodium, and the sodium gets collected by the second generations of stars. But as to how we end up having these stars form in the first 2 billion years, and why does it not continue on? Well, that is a very big mystery. So galaxy forms, and then the clusters will form. The clusters usually form on the outer edge. If the galaxy is spinning fast, particularly if it has enough angular momentum, then the globular clusters will sort of be outside the galactic disk. If it's more like an elliptical galaxy, it's not going to spin very fast. It's going to be able to push it down on itself, and then the globular clusters are going to be more evenly distributed around. Now here we get the difference in the classification. So out here, the globular clusters, the stars are more of the F2 and the F6 class, and they become a bit more of the yellowish stars as we move towards the G0 and the G5. So here we have the globular clusters that are a lot more hotter, and we get into the cooler globular clusters with the G-class stars towards the center. And any globular clusters inside here will be more of the K and the M class. So the hotter stars are towards the edge of the Milky Way, and the cooler stars are towards the center of the Milky Way. It's the same thing. We got hotter stars in the globular clusters out here on the edge of the halo. And as we get closer towards the center, they're going to be much cooler stars, lower temperatures. So the difference between the open and the globulars simply have no gas. They have lots of stars. They're physically round. They're going to have a cutoff where the stars will reach up to about F class, but they won't get any hotter, and then they'll just veer off into the supergiant stars. And they're very, very dense and more symmetric, where it's very irregular. They're restricted to the galactic plane for our open star clusters, and you can have all the way up to the O class stars, the very massive ones. What's the difference? What do globulars and open star clusters have in common? Well, they're held together by mutual gravity. All the stars will be about the same age. Stars in the cluster are at the same distance from the Earth. They're cooler stars. The colder the stars, the older the cluster, and they all orbit around the center of the Milky Way. The open star clusters, they'll contain bright blue stars. They'll contain hundreds of stars. They're irregularly shaped. Well, the stars here are lying in the halo or in the bulge. They're older. They're no longer forming. And they have tens of thousands to hundreds of thousands of stars, upwards of millions of stars. Now, we do have variable stars in these globular clusters. This is the RR Lyrae variable stars. There's the change in the pulse over time. You can see right here where we get an animated GIF showing the Lyrae stars there. Here's one right here that's pulsating back and forth. And this is with Messier 3. So this is with the globular cluster Messier 3. I don't know if anybody else can see any of these other types of, I tried looking for these other types of Lyrae stars in there that are brightening and dimming, brightening and dimming. I picked that one because it's the most prominent. But right here, one thing is that there's what we call the logarithmically scaled imaging, where we basically, what we do is that we can look at the color of the star based on its magnitude. So the brighter stars are a bit more bluish and the redder stars are a bit more faintish. And we find a range of magnitude, particularly between 10th and 19th magnitude, and that's going to be for this galaxy here for M3. I mean, for that globular cluster M3. And we can actually catalog these stars and use them as basically standards to measure the brightness of all the other stars in a globular cluster, and then look at the pulsation rate. Now here, we know about 274 variable stars. We can see how, as we change magnitude and brightness, it shows us the changes in the colors. This image was taken in a blue filter. This was done at the Moore Observatory in Kentucky. And you can see how the stars are brightening and dimming and brightening and dimming. So you get hundreds and hundreds of variable stars of at least different varieties within these globular clusters. And what's important is that here's M5, so we can see the flickering. So we got the RR Lyrae and the Cepheid variable stars right there. And we can actually use these as measurement indicators to look at the way that we can find the distances. We can measure the distances of these globular clusters. So we have what we call the period luminosity distance modulus. Basically, we look at the luminosity, we see the period. So here are the RR Lyraes, here are the Cepheids. We get two types of Cepheids that change in brightness over time. Here's actual data for one of those Cepheids. And one thing about the Cepheids is that we can actually do this. This is what used by Edwin Hubble to measure the distance of these Cepheid variables from our own galaxy, from Earth. So if we look at the change in the brightness, we can measure that as distance. So the change in brightness here, a good example, this is the Cepheid variable star V1. This was one of Edwin Hubble's variable stars. So here is sort of a map to find that star. Here's the color magnitude diagram for a globular cluster. Looking at the change in brightness. That change in brightness means we can use this formula here. And a difference in 5 magnitude between, let's say, 10th and 15th magnitude is 100 times in brightness. So this can allow us to measure the distance using that brightness change in those variable stars. And we can measure the distances of these globular clusters in parsecs. And a parsec is about 3¼ light years. Right here is the blinking of these stars. This is an M5. So we can look at the formula here. We can actually map out these variable stars. They fit within this island of instability, which is a phase as these stars pass through the main sequence. They become variables as they're giants and supergiants. So those variable stars are sort of reaching the end of their lifespan. So we can get the range of magnitude. These are the names for these stars in M5 and their brightness range, their periodic range. And we can distinguish them as Cepheids and RV Tauri, which are very common stars. So we get the distance, and we can measure that for M. I think I got that right, for M5. And we can see it has a distance of 24,730 light years, because this distance modulus is based on looking at the range of brightness between when the variable stars are bright and when they are dim. And we can get the age at 11.5 billion years old. And most of these stars are probably going to be in that G-class category based on that number right there. Now, let's be aware that globular clusters, their orbits will change over time. The orbital tilt will change. The periodic motion will change. So we look at the orbit with respect to the center of the Milky Way versus the plane of the Milky Way. And so the orbits do not maintain their shape. They sort of wobble around over hundreds of millions of years to billions of years. So the orbits of these globular clusters are much like the orbits of non-periodic comets. They will change over, in terms of the shape of the orbit, the tilt of the orbit with respect to the Milky Way, and how much time it takes for them to complete one circle around the center of the Milky Way. We can see the shifting. The meridional plane is just a different orientation of the Milky Way, but we can see that precessional motion does occur with these globular clusters as they move in and out of the plane of the Milky Way and shifting around the galactic halo. And some of them will move from the outer to the inner part of the galactic halo. This deals with the orbital velocities, and we have to say this, that the orbital velocities of these stars are much greater towards the center, and they're less when we reach out the edge. And that orbital velocity can be very wide. I mean, here on average for this is like 53.5 kilometers per second. But in terms of the change in the velocity between the stars, it gets less as you get further away from the center of these globular clusters. As for the radius, what this tells us is that we have mostly white dwarf stars and dead stars at the center, mostly white dwarfs, mostly pulsars and black holes, and mostly main sequence stars on the edge of a globular cluster. So a lot of the brightness you're seeing are those stars that are sort of surrounding the more denser concentrations of the dead stellar remnants, that is the white dwarfs, neutron stars, and black holes at the center. So we have higher velocity, we have lower velocities, mostly main sequence stars, taking longer time to orbit around the center of the globular cluster, while mostly the more massive stars, more of the white dwarfs, the neutron stars and black holes are at higher orbital velocities towards the center. This shows the dispersion of stars. So we have a denser number of stars towards the center. They're more clumped up together, where they're going to be more spread out because they have more space as we go out towards the edge of the globular cluster. This here shows that with light output, basically massive stars at the center, mostly these white dwarf stars, are not going to be very bright because most of their light, visible light, is in the ultraviolet. The lower massive stars, as we get further away, they're going to have a greater output of radiation. Whereas we get out towards the edge with these very massive stars out here towards the edge, the brightness is much less. Usually because these are stars of a lower surface temperature. Now, we can look at the stars, how they spin, because with globular clusters do spin on their axes. So we see these stars circling around towards and away from us, and that can vary between 3 to 8 kilometers per second for the stars that are moving towards us, and stars are moving away from us from our line of sight between us from Earth towards the center of the globular clusters. And most globular clusters, they spin around 3 to 8 kilometers per second. In terms of their motion around the Milky Way galaxy, in the first 10 kiloparsecs, in the first like 32,600 light years, they'll be moving around the Milky Way at about 50 to 80 kilometers per second. But then they'll reach about 100, 120 meters per second. That should be kilometers per second as we get further away from the center. And they're more in these prograde orbits versus globular clusters moving out. They'll be at different velocities, different orbital tilts. The velocity is more uniform towards the center, moving in the same direction, whereas they can move in opposite directions. That's in the case of our globular clusters within the Milky Way galaxy. Now, this is the color magnitude diagram. So we get our two generations of stars. What we find is that the 1G stars have higher amounts of helium. The 2C stars will have higher contamination of metals. So they won't be pure helium stars. That's because the heavier metals are being formed in the G1 stars due to during the first 2 billion years and when the stars are being formed. And this here shows the different globular clusters where we get the different types of stars that are forming because of the different amounts of calcium that exists within these stars. So the 1G and the 2G stars will have different amounts of calcium that resides within those stars. That's one way we can distinguish between the two generations of stars. Calcium is forming in the more massive 1G stars, so when they blow apart, the 2G stars will collect more of that calcium and they'll be more prominent in the spectrum. When we take the light and split it into its colors, we can look at the chemistry of these stars. Oh, so let's look at the pulsars. So this is actually a map here. This is actually a graph of all the different globular clusters in the Milky Way and the pulsars they have. So we know about 38 of the globulars have 292 pulsars. Some of them will be isolated, but there are such a thing as binary pulsars, where pulsars are actually grouped together as binaries. So you can get one pulsar moving around another pulsar. They're moving around their centers of mass. Now, the pulsars are very important because one thing astronomers are learning is that there's a magnetic field. You know how the sun has a magnetic field, the earth has a magnetic field? Well, the galaxy has a magnetic field. Well, that magnetic field appears to be, it's more uniform in its behavior on a grand scale, but at the smaller scale, there's a lot of turbulence. There's a lot of effects that are taking place in the magnetic field at the level of these globular clusters. And the nature of that is not very well understood. And generally, we don't have that magnetic field penetrating very deep within the galactic halo, but when it's penetrating deep, it's possible these globular clusters are altering the behavior of the magnetic field at the very small scale, because these pulsars are generating, what happens is that these pulsars have their own strong magnetic fields. And when a lot of these stars along the edge, the main sequence stars, are blowing out their material into space, it's being ejected out into the halo because of the effects of these pulsars. When they are really, the magnetic field of these pulsars are sort of intermixing within the magnetic field of our galaxy, within the galactic magnetic field, and it's creating this turbulence. The turbulence is causing the magnetic field to go in different directions. And that's creating this shock wave in which the gas being blown out from the more massive stars, from the main sequence stars on the edge of the globular cluster, is being pushed out towards the edge of the globular cluster, out into the halo. We know about 25 of these pulsars in 47 Tucana, which is really the big massive globular cluster in the Milky Way galaxy. If you've never seen it, you have to probably go south where you can see the Magellanic Clouds, because this is in the constellation of Tucana, right near, I think it's the Large Magellanic Cloud, one of the two major dwarf galaxies that isn't being torn apart by the Milky Way, that is close towards the Milky Way as satellite galaxies. Now we have to remember there's what we call the line of sight, because we can see it, the Milky Way galaxy, from one orientation, and then we see it in a different orientation, meaning that instead of seeing it this way, we could see it this way or this way or this way. But one of the important things is this line of sight, where we draw a line between the Earth to the center of the globular cluster. And what we find is that first, the field lines are traveling perpendicular to the plane of the Milky Way as they penetrate the galactic halo, and then they get bent as an angle when they're passing through these pulsars going through the globular cluster. The result is that it moves a lot of the ionized gas, because what happens is that a lot of these main sequence stars at the edge, they're very massive, they generate very powerful stellar winds, and like with Betelgeuse, they're shedding out their outer layers. Well, that material becomes ionized, and it ends up creating this shock wave, which bends the magnetic field of the Milky Way around the globular cluster. And what we get is that the magnetic field gets stronger, and we get a change in the direction of the magnetic field depending in which these globular clusters are going to be at one side or at the other side of the globular cluster with respect to our line of sight. So we have it on one side, we have it on the other side. So a globular cluster actually has two hemispheres, where the pulsars in one hemisphere are orienting the magnetic field in a negative direction towards a negative magnetic pole, and the rest are oriented towards a positive magnetic pole, from a south pole to a north pole. And the winds reach 200 kilometers per second. The globular cluster moves at 500 kilometers per second. And the net motion of the winds here are sort of helping move the globular cluster along. So we end up getting a total speed perpendicular to the galaxy of about 245 kilometers per second as the overall net motion for 47 Tucana. So Tucana is moving very, very fast. I mean, Imagine getting in your car and being able to go from Houston to San Antonio in a couple of seconds. Yeah, that's fast, very fast, but we have to remember that still takes hundreds of millions of years for a globular cluster to complete one orbit around the Milky Way. Now, black holes and stellar remnants. Well, with a less dense globular cluster, in the case of NGC 3201, this is in the Vela constellation, Caldwell 79. You can see it here from Texas. You'll just have to look low on the horizon to see the Vela constellation when it rises up, but it's visible in southern Texas. There's an indication here based on the simulations of the motions of the stars. Same way we look at the stars moving around the center of Sagittarius A star, the black hole, the center of the Milky Way. You see the stars circling around a region where there's nothing, but doing a bit of mathematics, we find that there's about 1,000 solar masses with a population of about 100 black holes. So we're having about 100 black holes, each of them about 10 times the mass of the sun. Now, no star is going to produce a black hole that's going to be more than a couple of solar masses. So what happens is that a couple of black holes formed from stars are going to collide together and form more massive black holes. There's also the concept of the intermediate mass black hole. What's an intermediate mass? Well, we got the stellar black holes, which are between 1 to 10 solar masses, a few dozen solar masses. Of course, those are probably formed from the less solar massive black holes colliding and creating the bigger massive black holes. And then we got the supermassive black holes and the hypermassive black holes between 1 million suns up to 10 and 100 billion suns. Well, in between, from about 10,000 to 100,000 or a few 100,000 times the mass of the sun, we get the intermediate massive black holes. I don't know if anybody's ever seen Andromeda's cluster, the G1 globular cluster that is near the Andromeda galaxy. There's some indications that it is a possible 20,000 solar mass central black hole. If you find these two stars, you can find that male too. I found it at the George Observatory using the East Dome 18-inch telescope. It's just a little sparkly fuzzball. And here's more indications of extragalactic black holes. They nearly exist in every galaxy in the universe, except for those near the giant elliptical galaxies. Like there's some galaxies that are near M87, which M87 has literally robbed those galaxies of their globular clusters. And I should say globular clusters exist technically in nearly every, I meant to say globular clusters existed. Yes, black holes exist in nearly every galaxy in the universe. I meant to say that globular clusters exist in nearly every galaxy in the universe, with the exception of the giant elliptical galaxies. Like M87 is swept up using its strong field of gravity, which extends for millions and millions of light years, has literally robbed many of the galaxies nearby of their globular clusters. And so it's estimated to have about 15,000 globular clusters. Here's NGC 147. This is one of the dwarf galaxies in our own local group of galaxies. So even the dwarf galaxies can have their own globular clusters. M32, M110 has their own globular clusters. Here's 4 of these. Here's some in NGC 2403. And you see where you see the number G here? This comes from Paul Hodges's Atlas of the Andromeda Galaxy. G. These are just among the 500 globular clusters we know that exist in the Andromeda Galaxy that we can map out. Now, the James Webb Space Telescope. I don't know if anybody's heard of the Sparkler Galaxy, but this is a galaxy that's been magnified due to gravitational microlensing. So we can see it in 3 different orientations because the light is being bent around by the more massive galaxies that are closer to us. So we see the galaxies that looked 9 billion years ago. You see all these spots right here, these red spots. There's about orange spots. Red spots. There's about a dozen of them. These are likely globular clusters that are forming. So they formed within the first. One thing about the James Webb Telescope, it's forcing us to reevaluate some of the theories of galactic evolution. One thing I'm curious about James Webb is looking at the origin of globular clusters and how globular clusters or forming at the very beginning of the universe, because looking at the dynamics of globular clusters can assist us human beings in perhaps providing new insights into galactic evolution and formation, particularly as they break apart from the original protogalactic cloud. So these were formed in the first 500 million years. The age is over 13 billion years old, so these were formed very, very early. The presence of white dwarfs can give an age of at least 12.5 billion years old. Look at the redshift value. So no wonder we're having to see this in the mid-infrared from 5 to 9, which means we don't have any image of this. If Hubble tried to look at this, it wouldn't see anything because this is all in the infrared. The current Z value places the distance at 13.69 gigalight years. So that's 13.69 billion light years. But we have to remember that space expands faster than light. So we see a galaxy that looked 13.5 billion years ago. We're seeing it at more than 40, 45 billion light years away. There's a poem from Hartley White, which is about I think it's the Rosetta star cluster. And yet may I phantom this vision deep, ere my life is rounded with a sleep. And that's it. So do we have any questions?
Excellent. Yes, we do. Thank you very much, Justin. Let me go to the chat. And Bill Spazzeri has a question. Bill, would you like to come off mute and ask your question?
Yes, that was fantastic, Justin. Before this, I would have said, yeah, I know about globulars, but I know a lot more now, that's for sure. Much more complicated than I thought. But you were showing the evolution, how they change with time, and how different stars. Specifically, you showed the distribution of the stars. I'm just summarizing here. White dwarfs in the middle, main sequence toward the periphery.
Yeah.
But that is an interesting structure, and I was wondering what that distribution of stars tells you about the globulars. There must be some reason why white dwarfs in the middle, main sequence on the outside. What does that tell you about the globulars?
Well, it tells us that with the first generations of stars, we call this the G1 stars. It tells us that there was more of a mass congregation. That is, most of the globular clusters' mass was towards the center, where the big massive stars were formed, and the less massive G1 stars would be spread out towards the outer layers of the globular cluster. And when those stars died, that dust got blown away by the intense radiation from the white dwarfs and the neutron stars, and from any of the radiation being emitted from the black holes. And that would form out towards the edge, forming the second generations of stars. Now, some dust got swallowed up by those black holes, and the black holes would collide together, and some white dwarfs and neutron stars can be torn apart by black holes to create more massive black holes and create those population of those stellar remnants towards the center, and the later generations of stars towards the edge.
Okay, so the distribution gives us a peek into the evolution of the cluster, in other words.
Yes,
right?
Based on the different populations of stars that come about in the first 2 billion years.
Okay, thank you. That answers my question. One comment I have is that I was thinking maybe you might mention it, but there was a science fiction story. You mentioned how the density of the stars, how close on average they are to each other in a globular compared to where we live. And there was a science fiction story by Isaac Asimov, 1940s, I think he wrote this, about what it would be like on a planet that was inside a globular cluster, because there's so many stars and it's so dense, they never have a nighttime there.
Oh, it would be daytime all the time. I mean, it would be like seeing 30 or 40,000 stars the size of a little spot of light like Jupiter, but being as bright as the full moon.
Right, and
but
so that means they never have any nightfall. That was the title of the book is Nightfall, because their astronomers did a calculation and said, holy mackerel, the things are going to be lined up just right, so we're actually going to have nightfall coming up soon, and everybody on the planet goes nuts because they're not used to that. Okay, so life in a globular is different, I guess, or at least Asimov thinks.
It would be, if you have the sun in the day, if you have your no home star in the daytime and the globular cluster at night, and depending how the planet spins, I mean, closer you are towards the center of the globular cluster, the more it's going to look like daylight all the time, with or without the mother star being up. But the radiation will likely kill you.
Oh, well, that's the other side of the coin. Okay.
Yes.
Very good.
Only because you have a lot of white dwarfs and black holes and neutron stars incredibly close.
Very close, yeah.
Yes.
All right. So kind of like the Southeast Texas right now, right?
Yes, and I'm not sure if there's a lot of terrestrial planets because even with the presence of calcium and sodium and oxygen, they're pretty metal poor stars, even with the Ostrov Type 2s, compared to our sun.
Thank you, Justin. Thank you.
All right. That was the only question we had in the chat. Does anybody have a question they've just thought of and would like to come off mute to ask it?
Any question will do. Don't be afraid.
Well, I'll tell you what I'll do. I'll ask a question, really kind of a point of clarification, Justin. So you have star formation from the primordial gas that is in that cluster, that collection of gas, and then you have those stars, those original stars, running out of fuel, collapsing, emitting whatever materials left in those stars.
Well, the stars will blow out their layers, and then there's a lot of radiation being produced from the stellar remnants.
And that will enable a second generation of stars to be formed. Is that
correct? That's the G2. The two main generations are the G1 and the G2.
And then after that, is there any more star formation, or is it so small that it's trivial? I mean, or is that kind of the end of the road for star formation?
Well, for 500,000 for a globular cluster to form all its stars in the first couple of billion years, that's pretty efficient in terms of star formation because it's usually just a couple of stars, usually every 100 years.
Mm-hmm. Okay. All right. Thank you. Okay.
I mean, the blue stragglers will be the ones that are forming in those globular clusters. They're moving through the Milky Way. Those are the only other stars that are being formed.
Okay. All right. Okay. Any other questions? Going once, going twice. Again, Justin, thank you very much. That was very insightful. I'm glad.
Thank you. It's been a long time since I've done one of these.
I'm glad we recorded it because I'm going to have to go look at it again because there was a lot of good information in there. All right. So to wrap up for tonight, I just want to make sure everybody's aware that tomorrow night is our general meeting at 7 p.m. on Zoom. And the topic will be light pollution. Mario E. Mata, Dr. Mario E. Mata will be presenting light pollution effects on human health and the environment. So if you do have time tomorrow, I ask that you join us. That ought to be very enlightening, pardon the pun, enlightening presentation. And with that, I thank you all for attending tonight, and I wish you a good evening. Thank you.